Recorded is rolling. It is Monday, February 5th. So you guys just turn in your kinematic review quiz. Thanks for that. I will get that graded soon. Your simple harmonic motion quiz is back in your folder. A bunch of guys picked that up for the bell ring. And the solutions I posted to Google Classroom. All right, so if you want to do corrections, then you guys got that opportunity. All right, today, main focus is going to be, we're starting a review for Unit 2 dynamics. So every week we'll review one of these AP sections. Here's a bunch of topics that I want to do with you guys related to Unit 2. Also, I'll give you guys some bonus stuff. On your desk, you guys see these thumbnail posters here. So this is what I'm doing with my honors students. There's a lot of topics that I cover with my honors students that I don't cover with you guys in too much detail because it's not going to be on the AP exam. But this is like a lot of things in this class, another opportunity. So extra stuff you guys can learn. Some of this might be relevant to maybe possibly some career paths you be doing, or maybe just curious, want to learn a little bit of extra stuff. So just point out what's here. One side there's things related to thermodynamics here. I have laws of thermodynamics and some related ideas, right? Different thermodynamic cycles, right? Pressure, temperature, phase diagrams. On the opposite side are concepts related to materials engineering. Got different principles here. We got stress strain diagram. If you do civil engineering, you'll see that all over the place. So yeah, there you go. So there's some extra opportunities, just things to know. That's just extra notes for you guys. Make some extra printouts so you guys can keep that. Right. Yeah. What I do want to do take a few days to go against off the path of AP is electricity. So when I do some electricity with my honor students, I'm planning to take a few days to show you guys about that, how circuits work. All right, so this. All right, so you guys got your notes out, right? So cell phones away, guys, phones away, notes out for reviewing the stuff. All right, so let's start with laws of motion. What does Newton's first law of motion say? Boom, there you go. It's the law of inertia. Okay. Object at rest, stay at rest. Object motion will maintain its velocity, which is both speed and direction motion. Okay. Unless or until some kind of external force acts on that object. You need a net external force to change that. Okay? And if you do have an external force acting on an object, that means it will cause it to do what? Accelerate. And that's Newton's second law of motion. Okay, since you guys have your notes out, I'm going to have you guys write a bunch of stuff. See if you guys stay a couple steps ahead of me. Write down Newton's second law of motion. Write down Newton's second law of motion in your notes. Did you guys write hopefully one of these equations? Okay. So acceleration is directly proportional to the net force on an object, inversely proportional to its mass. Right? See it one of these two ways. F equals ma. Okay. Now, when I say net force, an object might have like 10 different forces on it, but you can sum all the forces in each direction, like along each axis. What's the net force in the x direction, in the y direction, and sum it all back together, as if there's a single force acting on it. Okay. All right. So you guys said Newton's second law of motion. Oh, what about this? Oh, same pull this across the paper, right? And it takes let's say it takes 1 Newton to pull it. 1 Newton to pull it. All right, guys, is it pulling back on me at the same time? Yeah, but which is a greater force? I'm pulling it or it's pulling me? Which is a greater force? Equal. Yeah, and that is boom, Newton's third law. So because Newton's third law, whenever you here, guys, focus up here. Right? Whenever you have two interacting objects, like pushing or pulling at each other, the forces are always equal and opposite. Right? So how about this? Let me do sort of a counter example. How about it? All right, set this weight on the surface, right? Now this weighs about 5 newtons. Let's call it 5 newtons of weight, right? It's a downward force. So it's only through the surface of Earth, right? 5 Newton weight, straight in. Okay. Is the surface pushing up also with 5 newtons of force?
Yes.
Yeah, it is. Right. Now, is that because of Newton's third law? What about this? What if this whole podium was like in a elevator? Later on today, we'll get to elevator physics, at least I plan to, right? Get to elevator. What if this whole thing's accelerating upward at, I don't know, 3 meters per second squared or something? So it's accelerating upward, right? In that case, the weight of this object, does it still weigh 5 newtons? Yeah, still Earth's gravitational pull is still 5 newtons, right? But what about the force from the surface pushing up against it? What if there was like a scale down here, right? Pushing up. Would that still read 5 newtons? No, right? So what does that break Newton's third law? No, because you have to think about what forces are interacting, right? So when you say this thing weighs 5 newtons, that's the Earth pulling down on this object with 5 newtons of force, right? Guys, is this object also pulling up on the entire Earth? Yeah, but which force is bigger? The Earth pulling this down or this pulling up on the Earth? Equal, right? Because that's a Newton's third law pair, right? The Earth pulls down on this as much as this pulls up on the Earth, right? No, that's 5 newtons, 5 newtons, right? Now let's go back to the elevator situation. Suppose this is in the elevator and this whole thing is accelerating upward at 3 meters per second squared, right? So is that scale showing an apparent weight that's heavier than 5 newtons? Right, you guys think? Yeah, maybe we should, yeah, so be showing like an increased apparent weight, okay? Right, now the force interaction there is that this is pushing down. Here, let me get an exact number. Here. So I can do, see, it should be 5 newtons, right? But say if it's accelerating upward like 3 meters per second squared, right? It's showing like 6.5 newtons, something like that, right? Right. So the scale will be pushing up against us with 6.5 newtons. And this is also pushing down on the scale with 6.5 newtons. So between this and the surface, yeah, there is also a third law pair, right? But the one that you don't want to mix up is the Earth pulling this down and the surface pushing this up. That's now it's 3 different objects. So that's where there might be a mismatch, right? Okay. Right. So you guys get that, right? So this pulls down up on the Earth as much as the Earth pulls down on it, right? And this pushes into the surface as much as the surface pushes up, right? But if this was in an elevator situation, then those equal and opposite pairs would be different for those different scenarios, right? The Earth versus this, and then the surface versus this, right? Right. And then, okay, here's another third law, right? So say like the Earth and the Moon. Now, this is not exactly to scale, but just to get the idea, right? Even though they're different masses, they pull each other with the exact same force, right? With the exact same force, right? Oh, now, which one of these objects, the Earth or the Moon, is accelerating more? The Moon is accelerating more, right? It has a smaller mass, right? So that kicks back to Newton's second law of motion. Right? So equal and opposite force pairs, the same force on different masses, different accelerations, right? And in this case, it's not a linear acceleration; it would be a centripetal type acceleration, right? Because like going around. All right. Oh, all right, guys. Write down on your paper. What's the unit for force? What's the SI unit for force? Okay, 1 Newton, right? Yeah, so everybody in their notes wrote 1 Newton, right? You gotta measure force in newtons, right? And say 1 Newton equals, and what does that equal to in terms of base SI units? It's like kilograms, meters, and seconds. So 1 Newton is equal to 1 what? Kilogram meter per second squared, right? Right. So here, 1 Newton is 1 kilogram meter per second squared, right? And if you forget that, then just think back to Newton's second law of motion, because it's embedded right in that one, right? Right. Here's force in newtons. Here's mass in kilograms. Here's acceleration in meters per second squared. Boom, 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 boom. It's all right there, right? Right. How about this? How do you measure pressure in this class? Pressure. Pascals, right? Right. And one, there's other way too. You can do like atmospheres. You can do psi, but in this class, Pascal, because that's the metric unit. Right? 1 Pascal is equal to 1 what per what? Newton per meter squared, right? Right. Because it's a force per unit area, right? So there's some force spread out over some area. Yep. All right. So I got next here. All right. So I got a spring scale. I pull on the spring scale and it stretches some amount. Okay? How much is it going to stretch based on how much I'm pulling it? Can you guys write a formula for that? So you get an FRQ that, okay, you see a spring scale, you see it's being stretched. Can you guys write a formula that's ready to do that? That formula has a name. What's the name called? Hooke's law? Hooke's law? Right. Right. And what formula did you guys write for stretching a spring scale? F equals kx. There you go. F equals kx. Right? If you threw in a negative sign, that's okay too. If you said F equals negative kx, something like that. Right? Ooh, how about this? Right? as I pull this more, does it take some work to stretch it? Does it take some work? Yeah, so I'm doing some kind of force times distance. Now, the tricky thing is it's not a constant force, right? The more I pull it, the more force it takes, right? So the force is going up, right? So like if I stretch a centimeter there, it's not a whole lot of work. If I stretch a centimeter there, that takes a lot more work. It's a lot more force for the same distance. How much total energy is stored in the spring? That's to say that how much work did I do stretching it to this point? That's an equivalent value. Okay. Can you guys write down an expression for that in your notes? Right. So you have F equals kx. I'm thinking of a different formula, right? 1/2 kx squared. There you go. Is the work done stretching the spring is also equal to the energy stored in the spring. So here you go. Right. So here's maybe an unstretched spring here. Right. Here it is. I'm stretching it. Now the amount I stretch it, I'll call x. Might call it delta x. Sometimes you see some textbooks say that. Right? You could also go compression, right? I mean, these spring scales don't really compress, not really compress the springs, but there's a compressive spring inside this ballpoint pen, right? It's right here, right? Spring point point, right? Okay, so it could be either way, stretch or compress, right? So the quantity of force to stretch or compress that F equals kx, right? And then the energy stored in the spring. Oh, hey, look, if I put this on the graph, right? I got both of these formulas on the same graph, right? Different properties of the graph, right? The coordinate is Hooke's law plus kx, right? The area under the curve, that's the energy then stored in the spring. That's 1/2 kx squared. Okay, go ahead. And k, of course, is the what? Spring constant, right? How stiff is the spring? Right? You guys remember one day I had you guys take a bunch of these spring scales to figure out what's the spring constant for each one of these, right? I think they were in the hundreds of Newton per meter, or something like that, right? Somewhere there about. Right. You guys get so far? All right. We did lots and lots of free body diagrams. Right? We're just labeling all the forces acting on an object. Some textbook definitions say like also the moments that's like torques. I didn't quite get to later, right? All right, let's say we're looking at the forces acting on an object. All right, here's a bunch of scenarios. All right. So, how about this? Can you guys draw an outline of a rocket? Outline of a rocket in your notes, since you guys are drawing your notes. Right, you guys got cell phones away. You guys are drawing your notes, outline of a rocket. And let's say this rocket is in here, deep space at constant velocity. Let's say it's going like 10,000 meters per second, deep space. There's no significant gravitational forces nearby. Maybe there's some like distant planet where we're measuring the velocity with respect to, but no significant gravitational forces. Right? So 10,000 meters per second, right? Constant velocity, just going through space. Label all the forces. Draw the free body diagram for that rocket. Label all the forces on it. All right, you guys got it? I bet you do. And what'd you guys draw? No, nothing. That's right. Right. There are no forces, right? You could just be going. It doesn't need any forces to move, right? Hey, is that like Newton's first law of motion, law of inertia? Right? Could that be like a Voyager spacecraft just going? Right, just going, right? It doesn't need any forces to move. Right? Now, gotta shuffle some of these posters around. What about, here. What if you have a plane at constant velocity? Let's change this from a rocket deep space. Let's get rid of that. Right? Let's go a jet plane just going through Earth's atmosphere and also at constant velocity. So we're in the atmosphere of Earth. And let's say we're sitting on a plane like LA to New York. Right? So give you guys time to draw this free body diagram for a plane. A plane at constant velocity. It's driving across the states. I guess flying across the states. A plane at constant velocity. Okay. Now, constant velocity. Whenever you guys see constant velocity, what do you guys know about the sum of the forces? 0, right? Zero net force, right? So there could be forces, but they better all zero out, right? Okay. So you guys got all the forces drawn? What's one of the forces on your plane? Okay, yeah, it's weight, right? Mg, yeah, weight, right? Gravitational force. What's another force? Or yeah, the air drag. What else you got? Lift, right? Okay. And then probably some kind of thrust force too, right? Some kind of thrust force. Boom, boom, boom. Right? That should look something like that. So remember, constant velocity. I need all my horizontal forces or components to cancel out, all the verticals to also cancel out. Maybe something like that. could be a plane constant velocity. Right? All right. How about the one that looks kind of similar looking free body diagram is here. I have this lab weight here, spring scale. I just pull this lab weight horizontally across this horizontal surface at a constant velocity. Okay, so that's an area. Right. So yeah, so everything we got 4 forces. Right? There's the weight. Right? I usually label it M times G, right? Mass times gravity field. You could call it F sub G, right? Force due to gravity. See, that's a common one too. Right? There's the what's this force called? Normal force, right? And normal means what? Perpendicular, right? Like right? So if it's a horizontal surface, it'd be a vertical force, right? Vertical, right? And then you got some applied force from the spring scale, and then a friction force, right? And notice everything cancels out. The 2 verticals cancel, the 2 horizontals cancel, so that it's constant velocity. Right? Okay. How about this? Between this block and the surface, this block is made out of something. Right? Maybe it's this black paint that it's coated in, and the surface is something. Maybe it's this paper. So as I drag this across, right, there's some material property between those two called coefficient of friction, right? And if you look back at your free body diagram, coefficient of friction is the ratio of which 2 of these forces. Friction force and normal force, right? That's what this green box says right here. Coefficient of friction. Well, coefficient of kinetic friction. That's if it's actually sliding. Okay. Now it takes some initial force to overcome the initial friction, to break the initial static friction. Okay? It probably takes more force, right? And you'd have to build up to it. So if you put like a tiny amount of force, you get a tiny friction, and so on, right? Until it finally breaks the friction. That's like the static friction idea. Right? Okay, you guys remember all this too? Right. So this turns into an inequality because it builds up to that point. Right? And go back to these material properties then. Which of these is a bigger value? Coefficient of kinetic friction or coefficient of static friction? Think of that static right there. All right. Let's go through some examples. Right. Oh look, it's the same setup we were just looking at, right? So that's just copy paste, just smaller. Right? Oh, it's the same green box form and red box formulas, same one. Right. So let's say like wood and wood, for example. If you had a coefficient of static friction of 0.5, no, it's different kinds of woods. It's probably kind of a median value or something like that. Okay. That would mean that whatever the normal force is, you would need half of that to break the initial friction, right? But only 30% of that to keep it in motion after you've broken the friction, okay? After sliding. Okay? And then all the way down, you guys see pretty consistently, well, yeah, consistently all the way down, static friction greater than kinetic friction. Here's that. Right? Ooh, and these last 3 rows I got for like driving on the road situation, right? We're talking about an icy road, a wet road, a dry road, right? And yeah, the drier the road, the more coefficient of friction you get. So it'd be safer to drive because you have more control over the car. Right? Ooh, speaking of driving a car, here, I'll draw this along with you guys. Let's draw a car on a road. Let's just keep a horizontal road, nothing fancy. We'll get to inclines later. Right? Let's keep a horizontal road. Right? Let's say this car has a mass of 900 kilograms. It's driving at an initial velocity of 25 meters per second. It's about highway speed. Right? And let's say there's a coefficient of friction. Right? Maybe this car has anti-lock braking. Right? So if you had a car back in the 1970s and you slammed on the brakes, you're gonna skid across the road, right? Leave a trail of rubber, right? But if you have a modern day car, like 21st century, don't you have a computer system in your car called anti-lock braking, and it rotates the tires a little bit, right, so that it can maintain static friction, right? And let's say we're able to take advantage of that one, right? And let's call that coefficient of friction 0.80, something like that, right? What I want to know is, what is the braking distance of that car? Call it X. Right. What is the braking distance of that car? Right. You guys solve it. I'll solve it. I got the answer. Anybody else got the answer? All right. After doing this video at home, here, I'm going to hit pause and wait for somebody to get this answer. Record resume. Right, so Gavin's telling me 39 meters. All right, Gavin's claim is 39 meters. Let's see. So, step through this step by step. Free body diagram. This car have a weight, mg. Well, okay, 900 kilograms times 10 meters per second squared. I guess you could call it 9,000 newtons if you wanted. Right? I bet there's a normal force. Now, if it's just a level road, let's call that equivalent to this one so that the force is 0 vertically. So that would also be 9,000 newtons. And not because of Newton's third law, but because of equilibrium in the vertical sense. Okay? Right. And then this car is going to the right and braking. You guys think there's a friction force to the left? Right. If I did this exactly to scale, should this friction force be 80% of the normal force? Right? That's what I'm saying here, right? So let's call this 0.80 times 9,000 newtons, right? Because it's a coefficient of friction times the normal force, right? Let's say we're taking full advantage of the static friction in this case, right? So we can slow down as fast as we can possibly slow down, right? 8 times 9 is 72. What's that? 7,200 newtons, right? Ooh, but that's going to be important, right? Okay. So, how do you figure out? You know what? Oh, okay. So I'm about to be doing some math here, right? There's one number I gave you that's extraneous, that you don't need at all. That ends up canceling out. And there's another number you need that I didn't give you that's implied. Right? What number technically cancels out that you don't need? The mass of the car, right? What if this car was like twice as massive? Would it still be 39 meters, right? To brake to stop, right? Yeah, right. So I'll show you guys that later. Right? And then what value do you need that I didn't actually give you that might be implied? Earth gravity, right? Earth gravity. Okay, and final velocity would be 0. Right? I guess both of those. Maybe I should write both of those, right? So we got g of I'm just going to round it 10 meters per second squared. Okay, and yeah, you guys are right too. Final velocity would be 0 meters per second. That's right. Breaking to a stop, right? Okay. Good. Right. So I wonder how far it breaks. Hey, maybe if I got the acceleration of the car and then we jump back to kinematic motion, that would be one way to do it. Not the only way. We'll do another way too, right? I could do that way, true? Right. Can I do acceleration is net force on mass? Right? Would that be like 7,200 newtons acting on a 900 kilogram car? Is that 8 meters per second squared? Right. Also, if I want to apply directions, let's say to the right is positive, left is negative, that makes this negative. So it's at negative 8 meters per second squared. That's the rate the car's slowing down. Okay. Now, if I want to know braking distance, and notice I haven't mentioned how much time it takes to brake. I mean, right. So what kinematic formula do you think would get me there? First, second, or third? How about this one? Right. Okay, so here's our goal. Try to get this. Right? We know everything else. This guy's 0. Green. This is 25 meters per second. 0 is 25 meters per second. Square that. Plus
you get the 7,000.
Okay. That comes from yeah. So the question is, where does 7,200 newtons friction force come from? So friction force is coefficient of friction times normal force. If I take the full advantage of the coefficient of friction and then times the normal force, which is matches the weight of the car. Okay. So 80% of 9,000. Okay. That tells me 7,200 newtons. Okay. Boom. Okay. And then I got negative 8 meters per second squared. And I got this braking distance I'm solving for. Okay. So 25 squared is 625. Subtract that over 8 times 2 is 16. Divide that over. Right. There's going to be some number of meters at the end of the day. Okay. Plus x. Let's see what is x. Whatever 625 on 16 is. Oh, there you go. Exactly like Gavin said. 39 meters. There you go. 39 meters takes to brake. Okay. Like I said. All right. How about, you guys remember a few units later? Let's go ahead and skip to conservation of energy. There was a way you could solve this with energy also. You guys remember an open system, sum of energy initial minus work done by, well, friction in this case, equals sum of energy final. You guys remember that? Right? So what kind of energy did the car, I know this is a unit 4 review, but let's do it anyway. What kind of energy did the car start out with? Yeah, it was all in motion, 1/2 mv squared. Right? Now, minus work done by friction, is that friction force times stopping distance? And then if it's at a stop, 0 joules of mechanical energy at the end, right? Now, this friction force is, again, coefficient of friction times normal force, 1/2 mv naught squared. Okay, so I'm going to substitute coefficient of friction times normal force, and the normal force is equivalent to the weight. So I'll just do a double substitution right there. Okay. And then I said earlier the mass of the car would cancel out. Here's one place to show that. It cancel out 3 terms just by the mass of all of them. Right? Or you can plug it in, whatever. Either way, 9,000 kilogram going 25 meters per second. Square that minus 0.80. 9. Oh, sorry. Oops, scratch that. 900 kilograms. 900 kilograms. Oops. Right. So 9,000 newtons weight, and then x. There we go. That looks better. Right. So 900 kilograms. So the mass of the car. Okay. So subtract this over, divide that. Let's see if I get the same thing. So I'm gonna skip some algebra steps right here. Okay. Not 0.5 times 900 times 25 squared, then divided by all this 0.8 times 9,000. Yeah, I'm still getting the same number, 39 meters. Okay, right, guys got that? Okay. So there, we just found 2 different methods for the braking distance of the car, but we got the same number. Okay, right, guys go with that? Car braking to a stop. All right, car braking to a stop. All right, let's look at my poster version of this. You guys have thumbnails of all these. Right? It was way back in the day, I gave you guys 3 staple papers of thumbnails, right? So it'd be on that one. Right? This one looks like this. Hey, look at this. Tells you, well, okay, so this one tells you the rate the car slows down. So it gets you partway there, right? The acceleration of the car is up. Okay. That's fine. All right. How about draw an air hockey puck. Air hockey puck, boom. Say this thing is in motion with a constant velocity. All right, air hockey puck. Right. Can you guys draw the free body diagram for that air hockey puck moving to the right at constant velocity? What's one force on that puck? Yeah, it's weight. So I'll say mg. What's another force on that puck? Yeah, I'll call it force from the jets. Yeah, looks like a normal force. Are there any other forces on that puck? None that really matter, right? So I mean, maybe face a little bit of airbag or something. Usually we just kind of ignore that. Yeah. So yeah, so those would be the important forces. That's it. Right. If you just drew that, that would be correct. All right. Oh, that's that poster right there. Just right there. All right. You guys, any questions so far? Questions so far? All right, you guys ready for some Atwoods? Ready for Atwoods? Let's do some Atwoods. All right, Atwood time. All right, so Atwood going. Okay, let's throw a couple of masses on here, and then I'll give you guys 2 questions. Okay. So let's say this is mass A is 5 kilograms, and mass B is like, how about 7 kilograms? There you go, 5 versus 7. I've got 2 questions. What is the downward acceleration of mass B? And the follow-up question is going to be, what is the tension and the connecting string?
So is the thing massive friction?
Yeah, let's call this maybe an ideal pulley. Ideal pulley. Sometimes the phrase. Yeah. So yeah, massless friction. It doesn't have any rotational inertia or friction. Yeah, like that. They were just holding us up here. So it's like somebody holding on to this. Right. Let's hold it in place. It's just stuck there. Okay. All right. You guys solve it. I'll solve it. All right. Just again, I'm gonna. All right, so if you're watching this video at home, let me hit pause and then All right, got recording resumed. I think some of you guys tell me you got the answer. All right, what you guys got for the? Who feels confident about the first question? What you got? Anything? 1.67 meters per second squared. We got a claim for that. All right, you guys think so too? You guys think so? All right. What did you guys get for the tension in the string? What'd you get? All right, Gavin's saying 58.3 newtons. All right, yeah, that's what I got too. All right, so let's go through this. All right, so free body diagram. Now let's start with the external forces, right, which is just the two weights. Right. So do you guys think this is 70 newtons there? And you guys think this is 50 newtons right here? Right, you guys think? Okay. And then the internal force, just the string connecting everything together. Do you guys think that's sort of like the Goldilocks force? Has to be larger than the small one, but smaller than the large one, so this can accelerate like clockwise. Okay. And so I'm gonna try to kind of draw it that way. Okay. Oh, and also, do you think the tension is the same here and here? Right. Yeah, right. Good, because this is an ideal pulley. Okay. So FT. Right. Let's say we're solving for that. Right. I mean, here's the textbook answer, but we'll get to that. So different textbooks or instructors will go about these questions differently. Sometimes they have these solve system equations and like solve for the tension first. Okay. I always have you guys do macroscopic approach, like sometimes called a whole systems approach. You get the acceleration of the whole system first, right? Let's walk down, let's walk up, right? And then answer the tension question after that. So let's go just keep doing it that way because it's what we've always been doing. Okay. So from an external point of view, can I say that the acceleration of the system is the net force, net external force on the system divided by the total mass that's being moved by that net force, right? That's Newton's second law of motion, isn't it? Newton's second law of motion, right? So, here, you guys keep notes, right? So you guys see like a tug of war between these two external forces, right? So is that a difference? 70 newtons saying let's go clockwise, 50 newtons saying let's go counterclockwise. There's your net external force, right? Right. Moving how much mass? Yeah, 12 kilograms, right? 12.75 kilograms, right? 12 kilograms, right? So this should give us this value right here. See if it does. So 70 minus 50 is 20 newtons net force acting on 12 kilograms. Yeah, 1.67 meters per second squared. Okay. Now, of course, one block is going down, one block's accelerating down, one block's accelerating up, but they both have that same value of acceleration. Okay. Okay. Now, if you want to answer the question, something about tension in the string, this connecting string, what I would do is I would focus on either one block or the other block. Let's say I focus on mass A, right? And I say, well, there's an unbalanced force just specifically on that block, right? The tension up and its own weight downward, right? Let's go answer that. Right? So you guys getting this all in your notes, Right? So I'd say from the point of view of mass A, F net on mass A is equal to mass A times acceleration of A, right? And the net force is, well, I got the tension pulling up, which we're solving for, minus the weight down, which in this case is 50 newtons. Okay. It's equal to the mass of the block, which is 5 kilograms, times an acceleration of 1.67 meters per second squared. Okay. Now, if up is positive, I got positive there, and then its weight would be negative because it's downward. Okay, so all my signs are correct. Okay, so all you gotta do is take this and then add 50 newtons over. So what is 5 times 1.67? That's like 8.35 plus 50. I'm getting the tension force to be 58.35 newton. Okay, that's too much precision. and make it say about 58 newtons. Like if that was a multiple choice answer, that's probably what it would say. It's like 58 newtons. Right? Which of these is closest to, okay? Like I said. And then what if we want to do a check? Let's check from the perspective of mass B. Right? Let's do net force divided by total mass, and I bet we should still get the same acceleration. For just focus on mass B. Okay, so that's 70 newtons down, so it's open parentheses 70 minus. Now I'm making the claim here that the tension's like 58. I think it's like 58.333 is what kind of comes out to here. 58.3 something newtons. Right, pulling up. Right? Close that parenthesis. Divide by. Right, so there's my net force in parentheses. Acting on, in this case, 7 kilograms of mass. I'm just focused on mass B. Okay, so I'm applying Newton's second law of motion, but only to that mass. You guys get that? Net force divided by that mass. And there's only one number that can come up on my screen if everything's correct, which is what number?
Acceleration.
Yeah, there you go, 1.67. Okay, and that'll be meters per second squared. Let's see if it is. Oh, there it is. There it is. All right, here's those. Maybe let me change this to 5, see if it does. It's about the same. Okay, you guys got that? Boom. Alright, pick up next here. Boom, boom. Okay, let's show you guys the poster version of that going on. Right. So here's Newton's second law of motion. Right, here's here's all in terms of variables, right? This was just what we did to solve for the acceleration. Once we got the acceleration, we could go back and solve for tension. Now these two boxes, the updated poster, I colored these boxes differently. It's a little easier to see. Right? But here's Newton's second law of motion is it only applies to mass 1. Here's second law of motion is it only applies to mass 2. And either one of those, you wouldn't need both of them, but either one of those could solve for tension. Right? Although it's possible maybe you go to college and your college instructor actually starts with these two bottom boxes as a system of equations. Right? A lot of teachers actually do that. Okay? Yeah. All right. How about let's look at a modified Atwood setup. Right? So here's a really common one, right, where maybe one box is moving horizontally, so its weight doesn't really count as an external force because it's just immediately canceled out by the normal force, so you can just ignore it. Okay. Sometimes it's on little wheels or a frictionless surface, so there's no friction force, right? Or there might be a friction force, right? They could give you enough RQ where you can say, they give you this, they say there's a coefficient of friction of like 0.3, right? And then you would have to consider this friction force up here, right? Right. Now look at this, Newton's second law of motion. Here's, okay, now this plays out a little bit different than before, right? You got the weight down, and it looks like friction would be the other force slowing it down, right? So this hanging weight versus this friction counts as the net force for the whole system, right? Gets mass 1 and 2 added together is being accelerated, okay? And then you can find the tension of the string by either of these methods, okay? Guys got it? All right, let's do elevator physics. You guys ready for some elevator physics? So I have a poster on this too, but let's try this just on plain paper.
Okay. I didn't remember all these things.
Oh, many years I have been teaching. Yeah, that's yeah. So usually the best way to learn anything is to teach someone else, really. Yeah. So yeah. If you get to go with your friends or helping them out, it's probably the best way to learn. Okay. Let's say I have a guy standing in this elevator, and he's standing on a scale, and the scale's reading the normal force, right? Or you can call that his apparent weight, right? Or I might change the story and have like maybe a tension in the elevator cable. Now, whether I'm talking about the normal force on the scale or the tension in the elevator cable, right? The math is the same. Okay, you see that? Right. So, how about normal force on the scale is what I'm going to focus on. Let's say the elevator is accelerating upward. Let's have an upward acceleration. Can you guys draw the free body diagram on this guy? Free body diagram. Right, give you guys a head start here. Right. Did you guys draw a huge upward normal force and a relatively smaller weight? Right. And of course, like all these free body diagrams are connected to the center mass dot, right? So this force larger than this force, so that there's upward acceleration. Right. Let's give this guy a mass m. Right. Now, how are these forces and this acceleration and this mass all related? Right. I know we're kind of gets the bell here pretty soon, so maybe we'll try to get this in terms of variables. Right. Can you guys say net force equals mass times acceleration? Maybe start with Newton's second law of motion. So some version of Newton's second law. And the net force, would that be the normal force up minus this weight down is M times A? Right? And you might be asked to solve for any of these. Let's say you're asked to solve for what is the normal force reading on the scale. Can you guys go normal force reading is mg plus ma? Okay. And you could even factor his mass out, g plus a. Okay. Now that's true if you're accelerating upward. If you're accelerating downward, you just change this plus to a minus. It's like that's a shortcut. If this was a multiple choice question, it might be a good idea to memorize that, right? If you have a space in your mind, right, for multiple choice. But this is an FRQ. You better be able to derive this whole process. Okay, right? Here's a poster that has 3 scenarios: accelerating downward, accelerating upward, or constant velocity. Right. All right. You guys have a great Monday. Yeah, we'll continue review tomorrow.